Hello, let's begin with section 5.3, which is talking about the definite integrals and areas. So far, all the integration we've looked at has been indefinite integration, and now we will look at definite integration. Let's go to page 348 in your book and talk about what the definite integral is. Okay. First thing we need to look at, which I will explain a little bit later, is the fundamental theorem of calculus. Okay, it provides an easier way to calculate the definite integral using indefinite integrals. Okay, what is the definite integral? Okay, it gives us basically the area under a curve. Okay, so for example, if this is my function f of x, and I want to find this area, the shaded area here, under this curve between a and b, where a and b are my x values, okay, I can find this area, which I will show you using the integral. First let's approximate the area, okay? And we approximate the area using rectangles. We know how to find the area of a rectangle, length times width, so we can fit rectangles under this curve. So let's fit 5 rectangles. Excuse me. Let's fit 5 rectangles under this curve. So you can see when you fit these 5 rectangles, and just to note that these are called the left rectangles because the height of the rectangle is determined, is starting from the left edge. Okay, the left rectangle gives us an underestimation, and so this underestimation leaves some blank spaces, and these blank spaces is called the error. Okay. If we fit more rectangles, then you can see our error gets smaller and smaller, right? So the area under the curve approximated by 50 rectangles is more close to the actual area than if we use 5 rectangles. Okay. Let's go over an example of how to do this. So let's suppose they give us the function, this is example 1 in your book. Let's suppose the function is x squared, going from 1 to 2, and we want to approximate this area using 5 rectangles. And they tell us to use the left-hand edge of the rectangle. Okay, so let's go ahead and do this example. So here's the example here. Now what I've done is I have graphed this function. Okay, you can use your graphing calculator. And we want to go from 1 to 2. So that's 0. This is 1 right here. Okay, oops, let me make that better. And this is 2 right here. Okay. And we want to find this area. Okay, this area between the purple lines. Alright, so I always start out by writing the function and saying going from x equals 1 to 2, and they tell us to use 5 rectangles. And I'm going to write LHS, which means left-hand sum. Okay, so I can find the height of the rectangle. How am I going to find the width? Okay, well, the width of the rectangle is called delta x, which is the change in x. The formula for delta x is b minus a over n, okay, where n stands for the number of rectangles. So here that's 2 minus 1 over 5, okay, and so let me indicate this is a, this is b, right, that's your interval, and n is 5, and that is going to give me 1/5, which is 0.2. Okay, so now I think to myself, okay, if I start off at 1, then my next rectangle is going to start at 1 plus 0.2, which gives me 1.2. Then I add another 0.2, which gives me 1.4. Then I add another 0.2, which gives me 1.6, and then another, which is 1.8, and that's where you want to stop, because this is the rectangle 1, 2, 3, 4, and 5. Okay, those are my rectangles. So these I've already broken up by 0.2. So my first rectangle starts at 1, so it goes all the way up here. And then that's the first rectangle. Then the second one starts at 1.2, which is, here's 1.2, and goes across. Okay. Then the third one, I take 1.4 all the way up. So let me indicate this. This is 1.0, 1.2, 1.4, 1.6, 1.8, and 2.0. Okay. And then we go up. Oops. Let me draw this straight. Okay. Yeah, that's pretty good. And then that is. Okay, so then these are my rectangles here. So those are my 5 rectangles. So now let's calculate the area. Area is length times width. So here, or width times height. Okay. So I have the rectangles here. Let me calculate the height. Okay. So what is the height of this rectangle? Okay. Well, I know the function is equal to x squared. So this value here will be 1 squared. Just like this value here will be 1.2 squared. This value will be 1.4 squared, and so on. So let me write this here. 1 squared, 1.2 squared, 1.4. And you can put this in parentheses if you want. You don't have to. So basically you just take your values and plug them into the function f of x equals x squared. Okay. And we know that the area equals the base times the height. And I know that, and then I'm going to add them all up, right? Summation. So let's put a little summation sign here. So this means sum, right? Oh Lord, let me fix that. Don't know what just happened. Okay. And this means sum. Okay. So the first rectangle has a base of 0.2, right? That's what we calculated each of the widths to be. And then the height will be, let me do this. The height will be 1 squared. The second rectangle has a base of 0.2. Its height will be 1.2 squared, right? Again, remember, look at the height. The height here is how, where this point touches the function. It touches the function at 1.2 quantity squared, because that is the function. Okay? And then the third one is 0.2, so again the base times the height, 1.4 squared, plus the base, 0.2, times the height, 1.6 squared, plus the base, 0.2, times the height, 1.8 squared. Okay? Now question, why do I not want to go all the way up to 2? Why don't I take this out and say 0.2 times 2 squared, right? You might be wondering that. Well, look, we have, remember, this is a left-hand sum. Remember, that's what this said here, left-hand edge rectangles. So we have to use the left-hand edge. So you start at 1, and you go until you hit the left-hand edge of the, use the left-hand edge of the last rectangle. If I went ahead and did 0.2, then I would have to go all the way up to 0.2 and do another rectangle, which would give me 6 rectangles, and I don't want that. I want 5. Okay. If I was doing a right-hand sum, I would start at 1.2 and go all the way up to 2. Okay. So once you plug all of this into your calculator, you can get that this equals roughly 2.04. Okay, 2.04 units squared because it's an area, or you can say square units. Okay, so basically this is the example that's in your book. Okay, they've shown how to do this, and they've gone through and gotten 2.04. Okay. Now, if I wanted to do this with 10 rectangles, 20 rectangles, 50 rectangles, that would be pretty tedious, right? So actually, they've actually used a computer calculator to go ahead and give us the sum with different number of rectangles. And you can see that as the number of rectangles gets bigger and bigger, the sum of the areas of the rectangles goes to 2.333, or 2 1/3. So the exact area under the curve is actually 2 1/3, which we will verify later. Okay, let's go to page 351. So this is basically the procedure on how to find the area under the curve using rectangles. Okay. First of all, you calculate the width like we did, delta x. Here's the formula. You find the x values, okay, like we did before, because you add delta x every single time. So you start with what we started with, 1, and then you add. Remember, we added 0.2 every time. And then you calculate the sum. Okay, so you take the function of the first rectangle times the base plus the function of the second rectangle, which is the height, times the base, and so on. Okay, this is actually called the Riemann sum, named after the German mathematician George Bernard Riemann. Okay, the limit of the Riemann sum is actually the area under the curve. That is the definite rectangle. Okay, so remember, we've seen this before, this integral sign. Okay, this integral sign actually comes from the letter S. In old times, in old Europe, they used to write S like this, elongated, so this S stands for sum, because the integration is just continuous summation. Okay, and A and B, we haven't seen this before, but now when you put A and B, it's telling you which interval you're looking at the area of, or what interval you're looking at the area. Okay, and the limit as n goes to infinity. So if I did this procedure for an infinite number of rectangles, okay, then I would get the definite integral. Okay. This leads us to something known as the fundamental theorem of calculus. Okay, so now be careful here. You have to be specific in your handwriting. Capital F, okay, stands for the antiderivative or integral, and lowercase f stands for the original function. Okay, like here, the integral from a to b of f of x dx is capital F of b minus capital F of a, where f is the antiderivative. Okay, so I want you to somehow indicate, you use your handwriting to indicate capital F and lowercase f. Okay, they're two different things. So let's go ahead and write the fundamental theorem of calculus. Okay, and one thing here I want you to note here is that this vertical bar, so when you see this right here, x squared going from 3 to 5, that means you evaluate. So that's the notation for evaluation. You evaluate from 3 to 5. So you plug in 5 minus plug in 3. Okay, so we'll do some examples. Let me write this down first, the fundamental theorem of calculus. Okay. So the fundamental theorem of integral calculus says the following: the integral from a to b of f of x dx is capital F of b minus capital F of a, where capital F is the antiderivative of lowercase. Capital F is the antiderivative of the lowercase f. Let's box this, okay? This theorem is so important to calculus, we call it the fundamental theorem of calculus, okay? Let's do an example. So you'll see a problem like this. Integral from 1 to 2 of x squared dx. So this is what we just did. We approximated the area using rectangles. Now let's calculate the actual area. Okay. So this is, now how do we take the integral of this? Remember, you add 1 and divide by the new exponent. Okay. So that's what I'm going to do. Add 1, divide by the new exponent, gives me, uh-oh, I think my pen just died. Alright, so that is x cubed over 3, evaluated from 1 to 2. Okay. So now what I'm going to do is plug in 2 into this function. So now I've taken the integral already, and I don't need to repeat the integral sign. Okay. So this is 2 cubed over 3 minus 1 cubed over 3. And 2 cubed gives me 8. So that's 8/3 minus, remember we have to do this powers first. Remember our rule of exponent, order of operations, right? Exponents before division. So we do the exponents first. So this goes to 7/3. Okay. 3 goes into 7 2 times, and then you have 1 left over, which is 2 1/3 or 2.33. Okay. We can leave it as 7/3. And that is what the area of this function is. That's what the book told us, if you remember, up here. Right here. Okay. Is 2 1/3 square units. Okay. So this is, so 2 1/3. This is the area under the curve x squared from x equals 1 to x equals 2. Let's do another example. Let's find the area under the curve. Oops. So this is example 4 in your book. Let's see if I can scroll down. Okay. So this is find the area y equals e to the 2x from x equals 0 to x equals 1. So area, oops, this is example 4. Area under y equals e to the 2x, x going from 0 to 1. So I'm just going to say on the interval 0 to 1. Okay. So first thing we have to do is take the integral from 0 to 1, e to the 2x, and then dx. Okay, so the derivative, or you take the integral with respect to x. Okay, now remember how we integrate e to the ax? The integral of e to the ax dx is 1 over a e to the ax plus c. Okay, so you might be wondering why we don't write the plus c anymore. Let me put the plus c in and I'll show you what happens when you do that. So a here is 2, so this is going to be 1/2 e to the 2x. Okay, let's put that plus c. Okay, you're not going to, you don't put the plus c when you have definite integrals, but I'm going to put it in for you so you can see what happens to it. Okay, so we took the integral and now we're going to evaluate it from 0 to 1. Let me plug the 1 in. C is a constant. Okay, and then you do minus, remember this evaluation notation means minus 1/2 e to the 2 times 0 plus c. So e squared, so we get 1/2 e squared plus c, and then minus c, so the c minus c goes away. C minus c gives you 0. So that's why you don't need the plus c, because it's going to cancel out anyway. And then minus e to the 0 is 1, so this is minus 1/2. Okay, this is the exact answer. Okay, if you check the answer in your book, it might be written like this. Maybe they've combined the fraction and done e squared minus 1. Okay, so this is an acceptable answer, and this is an acceptable answer. Okay, if you want to know the decimal approximation, we can plug this into the calculator and get e, where is e? E squared minus 1 over 2. 3.19 roughly. Okay. So leave the answer, unless the homework or the test asks for the decimal approximation, leave your answer in exact form. Okay, so I'm going to put a little note here. Leave the answer in exact form. Okay. Let's do another example. So let's do the next example in your book. Example 5. Find the area under the curve f of x equals 1 over x from x going 1 to x going to e. Okay, so you want to find the area under f of x equals 1 over x from x equals 1 to x equals e. Alright, so again, same thing, integral. Now we're going from 1 to e of 1 over x dx. Now you remember the integral of 1 over x, that's the natural log of x, going from 1 to e. Okay, natural, so now we're going to plug in natural log of e minus natural log of 1. I don't need these absolute values here because e is a positive number, so the absolute value of e is e, and 1 is a positive number. Okay, the natural log of e is equal to, so let me put this intermediate step in there. So you got natural log of e minus natural log of 1. Natural log of e, natural log and e cancel each other out, they're inverses, so you get 1, and then the natural log of 1 is 0. So you're left with just 1. Okay. And again, notice I did not put the plus c's here. When you do definite integrals, you don't need the plus c's. Let's look at example 7 in your book. Okay, there's another example. You can review that on your own. It's pretty much similar. Okay. So remember we talked before about if I give you the total cost and you want to find the marginal cost is a rate. You have to take the derivative. If you want to go backwards, to go from marginal to total, you take the integral. Okay, so this is what this function is doing. a company's marginal cost function is given by this function, where x is the number of units. Find the total cost. So they're giving you the marginal, they want you to find the total, so that should tell you need to take the integral. Okay, x goes from 100 to 400. Okay, so let's look at this. So you'd write the integral from 100 to 400 f of x dx. Now how can I make the integration easier here? This is x to the negative 1/2, right? So you leave that 75 alone, add 1 to the exponent, negative 1/2 plus 1 is 1/2, divide by 1/2, which is multiplying by 2. Okay? Evaluated from 100 to 400. 75 times 2 is 150, then you plug in 400 to the 1/2 minus 75 minus 2 is 150, and then you plug in 100. Okay? And square root of 400 is 20, square root of 100 is 10, so your final answer turns out to be 1500. So the cost of producing units 100 to 400 is $1,500. So integration gives you the total accumulation of a rate. So if you want to go from a rate to a total, you have to integrate. Okay. Let's look at this one. Okay, in repetitive tasks, a person's productivity usually increases with practice until it is slowed down by monotony. Notice that this is the same thing in mathematics. The more problems you do, you'll be able to do those problems faster, right? With practice, your productivity will increase until you reach a peak where you can't do the problems any better than what you've been doing. But it will take a lot of problems and a lot of practice to get to that point. Okay. So let's look at this example. A technician can test computer chips at a rate of -3t squared plus 18t plus 15 chips per hour. T is the number of hours after 9. How many chips can be tested between 10 and 1? Alright, so let me do this one for you by hand. Okay, so they give us the rate, chips per hour, and they want us to find how many chips can be tested, right? So again, we're going from a rate to a total. So the only way to do that is to integrate. So we have to integrate this function, -3t squared plus 18t plus 15 dt. Okay, t is my variable. And I need to find the limits of integration, a and b. Well, it says the number of hours after 9 a.m. So 10 a.m. means that's 1 hour after 9 a.m. 10, 11, 12, 1. So that's 4 hours after 9 a.m. So t goes from, t goes from 1 to 4. Alright, and this is my function that I want to integrate. Okay. So again, you add 1 to the exponent, that's t cubed. Divide by the next new exponent, divide by 3, so that leaves me with just -1. Add 1, the exponent here is 1, add 1 to the exponent gives me 2, so that's t squared. Divide by 2, 18 divided by 2 is 9. And then the integral of 15 is just 15t. And this is going from 1 to 4. Okay? So now I'm going to plug in 4, and let me show you a more efficient way to do this on your calculator. Whoops. So here's my function. Y equals negative t, oh, we don't have t, we have x. Okay, cubed plus 9t squared, or 9x squared, plus 15t, or 15x. Okay? And I want to find when x is equal to 4 and when x is equal to 1. Right? So I'm going to go to second table set. Okay, it's on Ask already. And I want to find the value of 4 and the value at 1. So at 4, the value is 140 minus 23. Okay, So 140 minus 23 gives me what? 117. 117 what? 117 chips. So basically, if this many chips, this function, if this many chips can be tested per hour, then 117 chips will be tested between 10 and 1. Okay. Let's go to this, and they've pretty much done the same thing here. Okay. We talked about this, how summation, continuous summation is written by the integral sign, which is a stretched out x. Alright, Riemann sums. Riemann sums can be calculated for any continuous function, not just non-negative functions. The following diagram illustrates a Riemann sum for a continuous function that takes positive and negative values. So look at this function here, right? I can have the area under the curve here, and then I can also have the area under the curve here. When we say under, we mean between the curve and the x-axis. Okay, so this positive area here will this is the positive area, and this is negative area. So some of this area will cancel out some of this area. Okay, so when we have a function like this, you take the integral, you take the area of the top and the area of the bottom. So the area, positive area minus negative area. We will look at this in the next section. Okay. So that is all of this section 5.3. If you have any questions, please get in touch with me. In the meantime, work on your homework, and I will be posting the next quiz soon. Okay, thank you.